a very good evening to all the course participants. So this is the last lecture in the DLP program on satellite remote sensing of atmosphere. So today's topic is satellite remote sensing for fog retrieval and monitoring. So we will discuss in this section what is the importance of the fog and what are the different types of the fog and how we get the fog information from satellite data. Now, starting with the basic definition of the fog, fog is simply defined as a visible aggregate of water droplets which are suspended in the air and which reduce the visibility. And as per internationally accepted definition, when the visibility reduces to less than 1 kilometer, the situation is called as a foggy situation. And the fog is also defined as a cloud sitting on the ground, because the fog is very similar to the clouds. The only difference is clouds are at some altitude. However, fog base is on the ground. So this is the only difference. So fog is a very critical weather situation. That's why we need to study it. So due to the fog, there are many air, land and sea accidents, as you all are aware. And fog also delay the thermal dissipation of the temperature inversion, which leads to the trapping of air pollutant in the stable boundary layer. So let's understand what is a temperature inversion. So you know that in general, as we move high in the altitude, temperature reduces. So if you see this graph, this is the altitude versus the temperature. You see this red curve, this shows to the temperature. So as we move high in the altitude, the temperature reduces. This is a normal phenomena. But however, during the winter times, during night time, what happens is we get this blue kind of the curve. So in this curve, if you see, initially as we move high from the surface, temperature first increases and then decreases. So there is some layer or the level where the temperature is highest. So the area or the layer below this level is basically our stable boundary layer. Now, because this is a very stable boundary layer, it traps the pollutant. Now, how fog is involved in this? Because for the formation of the fog, this kind of the temperature inversion is required. So if this temperature inversion is there and then fog formation is there up to this level, then the dissipation of this layer will be less. Why? Because from the fog top, there will be the reflectance of the solar energy. So solar energy will not be able to reach the surface of the earth and it won't be able to warm this point on the earth's surface. Therefore, it delays the dissipation of the temperature inversion and hence it leads to the trapping of the air pollutant in the stable boundary layer. Now let's understand how this layer basically forms. So what happens is, there is always the emission of the radiation from the surface of the earth because of its temperature, right? And also there is the incoming solar radiation. So during daytime we have incoming solar radiation as well as the emitted radiations. But during the night time we have only the emission of the radiations from the earth's surface. So this is true for the summers as well as winters. But what is special about the winters is, in the winters we have very long nights. Our nights are longer than the day. So the dissipation, or you can say that the emissions have the more time. So for the more time, there are emissions from the Earth's surface leading to the cooling of the Earth's surface to little more extent, which leads to the cooling of the air near the surface by the process of the conduction. So in the winters, during the night time, air gets so cold that the temperature near the air reduces to the temperature even below levels, even at the above levels. So therefore, because of the longer nights and hence the emissions of the thermal radiations from the Earth's surface, we have the temperature inversion in the night time of the winters. Then also we know that due to the climate change, there are changes in all the geophysical parameters. And also there are the changes in the fog pattern, that is the duration of the fog, formation of the fog, dissipation of the fog. So all these changes in the fog can also significantly affect the thermal radiation balance of the earth. How? Because if suppose there is the increase in the fog formation, then what will happen is the more reflectance will be there, incoming solar radiation will be reflected. So it will lead to the cooling of the earth. And suppose if there is the reduction in the fog formation, then the reflectance will reduce, so thereby leading to the warming of the earth. So that's how fog have the significant effect on the earth radiation balance also. So considering all these important things related to the fog, we understand that the study of the fog is very important. To study the fog, we need to have the measurements of the fog. Now, for as usual for any other parameters, we have the ground ways of measurement of the fog. So fog is measured in terms of visibility. So for visibility measurements, there are two ways. One is the manual way and another is the automatic way from the ground stations. So manual way is a person go and see how far he can see. For example, he can see up to 100 meter, 200 meter, 500 meter, and then he will note down, so up to how far he can see. So if he can see up to 1000 meter only, so that condition will come in the category of fog. If he can see beyond 1000 meter, then it will come in the condition of non-fog. And for the automatic measurements, the instruments are used. The ground-based instrument which is used for the automatic measurement of the fog is called as transmissometer. Actually, transmissometer is consisting of two instruments. One is a transmitter and another is a receiver. So transmitter sends some signal which after passing through the atmosphere in the horizontal direction, of course, then it is received by the receiver. So depending on the visibility or depending on the presence of the fog, there will be some dissipation of the signal which has been sent by the transmitter. So now that dissipation will be studied by the receiver. So more dissipation means the more fog or lesser visibility. So that's how transmissometers are used for the automatic measurements of the fog from the ground-based observations. But as usual, all the in situ measurements, which are called as the ground-based measurements, are always limited in number. We have very sparse data, only few data points we may have. Wherever we have the instrument, only at that location we will get the observations. And then the installing of such kind of the instrument is mainly possible over the land areas and the areas which are not remote, right? So because over the remote areas and especially over the ocean area, we cannot have the such instruments. So we have very limited measurements over the land area only, and we don't have the measurements over the remote areas, and very, very less measurements over the ocean areas, because in the ocean area, you will have the measurement points wherever you have the shipping lanes. That's it. And again, the ground-based observations are reduced during the night time. Nighttime measurements are further reduced because of its own complicacy, right? So therefore, due to the limitations of the ground-based observations, we have to switch to the satellite-based observation. So getting the fog information from the satellite is very important. So we will discuss how you can get the fog from the satellite after few introductory slides. Now let's see what are the factors which influence the fog formation. So first is the relative humidity, which is defined as the ratio of the amount of the water vapor actually in the air compared to the maximum amount of the water vapor required for the saturation at a particular temperature, right? And we know that for the saturation, the relative humidity should be 100%. That is, if there is any additional water vapor you will put, the condensation will take place. Then you're coming to the saturated air. This is the air that contains the maximum amount of water vapor that is possible at a given temperature and pressure. Of course, the saturated air would have the relative humidity of 100%. Then third one is the condensation nuclei. These are the nuclei on which the water vapor can condense, right? So if condensation nuclei are present, then even if the relative humidity is not 100%, the condensation may start because these nuclei facilitate the condensation, right? So if we have the smoke and dust present in the atmosphere, the condensation may occur even if the relative humidity is about 80 to 85%. However, if the condensation nuclei are not there, then for condensation we need to have the relative humidity as a 100%. Then dew point temperature, it is a temperature to which the air should be cooled for saturation to occur with no change in the air pressure or moisture content. So that is, suppose if you have an air parcel, you start cooling it, but without changing of the moisture content or the pressure. So a time will come when relative humidity reaches 100%. So that point temperature is called as dew point temperature. Now we will discuss some more phenomena which are a little bit close to the fog: dew, frost and haze. We'll just briefly discuss about these three things as these are very close to fog. First coming is the dew. Dew, as we all know, this is very common on the vegetation in the early morning after a clear night. So now what happens during its formation, that is how the dew is formed. So what happens is during clear calm nights means a cloud-free nights, means when we don't have the clouds in the sky. So during such clear calm nights, so what happens is there is a lot of emissions from the Earth's surface which are not trapped by the cloud present above, right? So if cloud is not present, so emissions will not be trapped and the surface of the Earth will be cooled to little more extent, right? So thereby it will also cool the air which is close to it, right? So air in contact with this surface will also cool by conduction. So if you have the sufficient time, so air may cool to dew point also, and which is true especially during the winter times. We have the sufficient time and air get cool to dew point temperature, and then what happens is water condenses onto the cold surface and appear like a water droplets, and this kind of the water droplets on the surface is called as a dew, right? It happens on the clear nights only because already discussed, because the emitted radiations are not trapped by cloud cover. Further, the dew forms on the vegetation mainly because vegetation cools more quickly than any other surface, because vegetation has lower heat capacity per unit area. Therefore, the cooling will be faster in case of the vegetation as compared to any other surface, for example, road surface. So usually we see the dew forms over the vegetation after a clear, calm night. Then coming to the frost. Frost is formed if the dew point is below 0 degrees Celsius. This is now called as a frost point, right? In this case, what happens is a water vapor directly changes to ice, right? So this kind of phenomena usually occur in the higher latitude region. It does not occur in our tropical region. Then coming to the haze, so we may have the dry haze, we may have the wet haze. So dry haze often occurs when there are the dust and smoke particles accumulated in the air. So when the weather condition blocks the dispersal of this smoke, they concentrate and hang in the lower altitude, which reduces the visibility, right? So presence of the haze also reduces the visibility. So, but if there is no water vapor, then it will be called as a dry haze. So if there is some water deposition on the dry haze particle, then that is called as a wet haze. So there's a difference between the wet haze and dry haze. So dry haze does not have the water vapor. However, if there is a water vapor deposition, then it becomes a wet haze. So haze also reduces the visibility, but visibility will not be less than 1 kilometer. Visibility will be something like 2 kilometer or 1.5 kilometer, like that. So that is haze. Then coming to the finally the fog formation. So in case of the fog formation, what happens is the air cools during the night. So if air will cool, definitely relative humidity will increase, because cooling of the air means we are reducing the temperature. If you are reducing the temperature, relative humidity will increase. So if the relative humidity reaches around 75%, water vapor start condensing onto tiny condensation nuclei, right? And the particles become large. So if these particles are large enough to scatter some visible light, so it will reduce the visibility, right? But because the visibility reduction is a bit, means at least 2 kilometer is there. So up to that point, that situation will be called as a haze. However, if the relative humidity keep on increasing, that is if air keeps on cooling during the long nights, these haze particles will grow larger, and also the condensation will begin on the lesser active nuclei. So increasing size as well as the concentration of these active nuclei or the droplets, the visibility will further reduce. So once the visibility reaches to 1 kilometer or less than 1 kilometer, then we call this situation as a fog, or we say that the air is wet and the haze becomes the cloud resting on the ground, which is called as a fog. So what are the necessary conditions for the fog formation? So we can easily understand one basic condition is relative humidity should be very high. Second is winds should be light. Wind should not be more than 2 to 3 meters per second. See, if winds would be high, then what will happen is there will be lot of mixing. So a saturated air will immediately mix with the unsaturated air and condensation will not take place. So winds should be light. Surface should be cool, that is also obvious. And last one is there should be temperature inversion. So we have already discussed how the temperature inversion phenomena take place during the winter times. Night duration is very large, so emissions will be very high. Temperature of the surface will be reduced, thereby reducing the temperature of the air near the surface. Therefore, we have the lower temperatures near the surface as compared to the temperatures at a little higher altitude. So this kind of the profile is basically called as a temperature inversion. So this is also one of the necessary conditions for the fog formation. And the fog always forms below this point top of the inversion, right? This fog top will be at the top of the inversion. So usually the fog thickness would be from surface to the top of the inversion. Now coming to the classification of the fog. Fog can be classified into various types depending on the process of formation, depending on the visibility, as well as depending on the appearance. So depending on the process of the formation, we have 5 major types. One is a radiation fog, another is a advection fog, then mixing fog, steam fog, and frontal fog. And depending on the visibility, we have dense, moderate, and thin fog. And depending on appearance, we have smoke, smaze, frost smoke. Now we will discuss briefly each type of the fog. First coming is the radiation fog. In the case of the radiation fog, the process of the formation is same that we have discussed till now. There will be the emissions of the radiation from the surface at the night, which cools the bottom air, right, until it reaches the saturation. So once it reaches the saturation, condensation will take place. So initially, of course, a thin layer of the fog will be formed, but after that, again, there will be the emissions of the radiation from the fog top, which will reduce the temperature of the air above the fog, leading to the thickening of the or deepening of the fog layer, right? So radiation fog is one of the important type of the fog which is there over the Indo-Gangetic plain. And the thickness of the radiation fog is maximum around the sunrise, because after the sunrise, the sun's radiation start falling on the fog top and start warming it. That is, the fog will start dissipating after the sunrise. Then coming to the advection fog. So as the name suggests, there is some horizontal movement of the air. So in case of the advection fog, what happens is warm, moist air moves over a cold surface. There is some cold surface at some point on the earth. So from the adjacent areas, some warm, moist air will come over the surface. So when the warm, moist air come over the cold surface, that air will cool down by the process of the conduction from the earth's surface. So if the cooling is sufficient that it reaches the dew point temperature, that is the air is saturated, then the condensation will take place. So advection fog is also one type of the fog which is there over the Indo-Gangetic plain. So in case of the advection fog, horizontal contrast in the temperature is very important. There must be some temperature contrast in the horizontal direction. Then we have the subgroup of the advection fog, which contains the sea fog, tropical air fog, and upslope fog. In case of the sea fog, as the name suggests, sea fog is over the sea area. So in case of the sea fog, the warm moist air move over a cold oceanic surface or the cold sea surface. Now because the warm moist air will be in contact with the cold sea surface, it will also cool down, and if the cooling is sufficient, that air is saturated, then condensation will take place, and such fog will be called as a sea fog. Then second is the tropical air fog. In this case, there is the flow of the air from the lower latitude to higher latitude region. So we know that as we move from the lower latitude to higher latitude region, there is the temperature reduction. Temperature decreases. So when the air will move from the lower latitude region to higher latitude region, so because of the contact of the lower temperature of the Earth's surface, air may cool down to dew point temperature, leading to the formation of the fog. Then coming to the upslope fog, again as the name suggests, it forms over the slopy areas. So it forms when the warm moist air moves along a hill or a mountain or some elevated plains. So what happens is when the air rises, it will expand. Expansion leads to cooling, and if the cooling is sufficient and there are the sufficient moisture which leads to the saturation of the air, then fog formation will take place. And such kind of the fog is called as upslope fog. So these are the three varieties of the advection fog. In all these three types of the fog, there is the movement of the warm moist air over the cold surface. Although this movement is in the different areas, but yes, there is a movement over a cold surface. Then coming to the mixing fog. Mixing fog occurs when the warm moist air come in contact with the cool moist air, right? So of course, when these two types of the air, warm and cool moist air, will combine together, right? And there will be the cooling of this air, right? The cooling is there, but moisture is also there. So there is a possibility that the total parcel, the mixture, may reach to the dew point temperature and fog formation may take place. Such kind of the fog usually occur at the fronts between the air masses of maritime origin. So a very special case of the physical process associated with the mixing fog occurs when we see our breath during the winter times. You all must have seen when we breathe during the winter, we just see a small fogginess just outside our mouth. So what happens actually is from our lungs, a warm moist air comes out, which mixes with the colder air outside, because during the winters, the air is very cold. So the warm moist air from our mouth, it mixes with the colder air outside. So for some moment, the mixture becomes saturated and condensation take place, and we see some fogginess just outside our mouth. But immediately, this air which is outside our mouth, it mixes with the further drier and colder air, and then there is no longer saturation exists. So we see fogginess just outside our mouth, because after that, that air further mixes with the more drier air until there is no saturation. Then coming to the steam fog. Steam fog is produced by intense evaporation of water into the relatively cold air, right? So water is evaporating into the cold air. So when the water is coming to the cold air, so its temperature will reduce. So temperature may reach the dew point temperature, which leads to the saturation and hence condensation, and the fog formation may take place. So steam fog is observed over the bodies of water in mid and high latitude regions mainly, because the coldness is more in the mid and high latitude region. Then the last among the processes is the frontal fog. Frontal fog is found along the boundary of two air masses of different temperature. When the say warm air mass and moist air mass come in contact, so at their boundary there is a possibility that the temperature may reach the dew point temperature, and hence the fog formation may take place. So these were the 5 types of the fog depending on the process of the formation, that is the radiation fog, advection fog, mixing fog, steam fog, and frontal fog. So out of these 5 types, radiation fog and advection fog are the 2 main type of the fogs which are found over the Indo-Gangetic plain, that is in our Indian region. Then coming to the classification of the fog based on the visibility. So depending on the visibility, we have simply the dense fog if the visibility is less than or equal to 45 meter. We have thick fog if the visibility is up to around 450 meter, and the fog is called as a moderately thick fog if the visibility is around 900 meter, and the fog is called as a thin fog if the visibility is as high as 1.8 kilometer. Then the classification bases on the appearance. Depending on the appearance, we have again 3 types of fog. First is the smoke. So smoke is nothing but smoke plus fog, mixture of smoke and fog. Then coming is the smaze. Smaze is a mixture of smoke and haze. Then is a frost smoke. So as the name suggests, this frost means we have something which is directly converting from vapor to ice, not going in the liquid phase. So this kind of the phenomena usually occur in the high latitude region and mainly in the Arctic region. So what happens is when the air temperature falls below freezing point and the water in the sea is not allowed to freeze, a kind of the fog consisting of ice is formed. And this kind of the fog then carried to land by winds. So this kind of fog is called as a frost smoke, but this usually occur in the high latitude region. So now after understanding the basic concept of the fog, its formation, necessary conditions required for the fog formation and different types of the fog, now we are coming to the fog detection using the satellite data. Now first of all, I'll show you the true color satellite images. Now these are the basically MODIS images. Now let's say the first image here. You can easily see the Indian region. So this is the mountainous region, very clear. So these are some cloudiness there. This white patches are basically nothing but the cloudiness. Now how we will distinguish whether this is a fog or the cloud? So if I see this area, oceanic area, so in the ocean area, any whiteness is of course this is a cloud because ocean is anyways, otherwise it is water. This is snow or cloud. This is a snow because it is following the topographical pattern. If you see, this pattern is actually following the mountainous region. Some mountainous texture is also clear. So this is a fog. Now we are, this is the snow. Now we are coming to this part and this part. This all is the cloud basically. But if you want to see whether this cloud is a fog or not, although fog is a type of cloud only, but it has some different characteristic than the other type of the cloud. The fog is a cloud at the surface, that's it. But other type of the clouds which are not on the surface of the earth, they do not have the smooth cloud top. So if you see the part over here and here, this top is very smooth. However, the top of this white patch is not smooth. Even the top of this white patch is not smooth. So this is definitely not the fog. This is cloud. So this patch is basically nothing but fog. And moreover, we know that is a winter time. That is a December 17, 2019 winter time. So this must be fog. And also this is following a topographical feature. This is just, if you see, its boundary is basically the foothill. Right. So this from here hill starts. So this is just fog is below the foothills. So it is starting from the foothills. So this is also one way to see this is a fog. Then there's another image, 16 December 2019. Then this you can see the pattern of the fog has changed. Now this image, which is of December 23, 2018. Here if you see, we have only a very, very small patch of the fog. That's it. The rest of this basically is nothing but a haze. This small haziness you can see over here. This is nothing but haze. So these are the true color composite, but this data is from the MODIS, which is on the polar satellite. So we get data only once a day, although the satellite is giving the data twice a day, but one time is during night time. So nighttime data is not useful because we need to see fog, which is a visible channel. We need visible channel to see the fog, so which is available only during the daytime. So we get data only once a day using such kind of satellites. So which is not sufficient, and you know that this MODIS is basically past time is around 10:30 a.m. So this is just 10:30 a.m. image. So if I want to monitor the fog continuously, then I need to go to the geostationary satellite data. So among geostationary satellite data, the option that we have is the INSAT 3D and INSAT 3D. Now you see this is the one image which is from the INSAT 3D imager. This is the thermal infrared band of the INSAT 3D imager, and the time of the image is 12 UTC, that is 5:30 in the evening. I hope you can see this is the Indian region in the image. This is the oceanic region. Here you have this Bay of Bengal, Arabian Sea. This is the Indian Ocean. And this is the mountainous region. This is nothing but clouds, right? So this is snow. Now where is the fog in this? So if you see little clearly over here, this is a small, very dark gray patch is there. This is basically fog. How we can say this is the fog? Its top is very smooth, right? And its temperature is very high. See, this is the thermal band. Thermal band is also representative of temperature. The brighter part on the image corresponds to low temperature, and darker part in the image corresponds to high temperature. So fog top will have the high temperature because fog is lying on the ground. But fog top have the temperature which will be little less than the ground. So there will be small contrast of the fog top temperature with the land surface. So this is the land surface, this is the fog. So visually we can see, but if you see, it's very difficult to distinguish the fog from the other features, especially the land feature, because the contrast is very poor. So what we need to do is we need to develop some methodology which can distinguish this fog from the other feature. So what we want is, we want to get this kind of the image from this image. Means we want to remove all these other pixels which are corresponding to all other features, and we just want to get the foggy area separate from the other part of the image. So now we will discuss how we actually do that. So I will discuss the methodology for the getting this kind of the fog images, and we call this process as a retrieval. When we try to get a particular parameter from the image using the mathematical techniques, we call that process as a retrieval. So that's why we have written over here the methodology for the fog retrieval. So I will take the example of INSAT 3D imager to describe the methodology of the fog retrieval or the fog detection. So in the left hand side table gives the channels of the INSAT 3D imager. INSAT 3D imager has 6 channels: visible, swirl, mid-IR, water vapor, thermal 1 and thermal 2. So for this methodology we shall be using visible and thermal channel, right? So moreover, in case of the fog retrieval, we have separate methodology for daytime and nighttime. So that we will discuss why. But first we will discuss what is the daytime methodology for getting the fog information from the given satellite data, right? So in the given satellite data, what all we have? We have clouds, which includes mid-level clouds, high-level clouds. We do have snow. We have the bright line pixels, we have land features, and we have oceanic features. So what we want to remove all these features, right? So we will use the physical properties of fog and the other features to remove all other features except the fog, right? So first we will try to remove the high and mid-level clouds from the fog. So what we know about the high and mid-level clouds? High and mid-level clouds have low temperature as compared to fog, right? So which channel gives us the information about the temperature? This is a thermal channel. So we'll use thermal channel to remove the mid and high level clouds. So people have done some experiment and they have concluded that all the mid and high level clouds have brightness temperature less than 270 Kelvin. So what we will do, we'll take our thermal image and we will put a threshold of 270 Kelvin. That is all the pixels having the BT that is the brightness temperature, less than 270 Kelvin shall be removed. That is, all the pixels corresponding to mid and high level clouds shall be removed. Then we are coming to the step of removing the snow and other brightline pixels. Other brightline pixels include the desert area. So now how we will remove all these pixels? So we know the feature of these pixels is these have the high reflectance. Snow as well as the desert areas have very high reflectance in the visible channel. So we will use the visible channel and we will remove the pixels with the very high values of the reflectance. So we have to again determine a threshold for this purpose also. So people have done experiments and develop a threshold of 35%. So all the pixels with the reflectance value of more than 35% shall be removed. That is, all the pixels corresponding to snow and brightline shall be removed. So now after removing the high level clouds and mid level clouds and snow, we shall have the image which is containing the fog and land features mainly, right? So now fog is something that we want and land features are something that we want to remove. Now how we will remove the land features? For that, first we will generate an image containing only land features. When I say only land features means we just want to remove the clouds, right? So such image which won't have the cloud will be called as a clear sky image. Clear sky image means an image which is there without any cloud. But how we will generate it? What we will do is we will take the visible images of last 15 days. Say for example, you are doing all this process for say 9 a.m. on say November 16. Right? So what I will do, I will take 9 a.m. images of all the 15 days from November 1 to November 15. This I will do. Then for each pixel, I will see all the last 15 days and will keep that pixel which have the lowest reflectance. Right? For each pixel, I will keep the value of those that day which have the lowest reflectance. And we know that the lowest reflectance will be corresponding to land feature. So the image that will come after using these 15 days of data will be clear sky composite image. So here one assumption we are making, the assumption is in last 15 days, at least for one day, each pixel will be cloud free. For example, if there is some pixel which is not cloud free for all the 15 days, then we won't be able to generate the clear sky composite. But usually in the 15 days, each pixel is cloud free at least for one day. So we get the cloud free image, or we can say that the clear sky composite image, that is the image which will be containing only the land feature. So what we'll do, we will subtract this image from this image. That is, the image with the fog and land feature is subtracted from the clear sky composite image. So this is a differencing. Then this differencing basically give us finally the image with the fog, right? So this is actually the good fog image, but because of the limitation of methodology, which is always there with all the methodologies, there will be always be some residual high mid-level cloud, snow, and other features will be there. So to remove these residual features, we will apply some test. First is the spatial homogeneity test and second is a temporal consistency test. The spatial homogeneity test, what is done is, we will take a 3x3 pixel of the image and calculate the standard deviation. So if the standard deviation is more than a threshold, then that pixel will be rejected. The basis of this test is the physical feature of the fog, which is the fog top is smooth. We know that the fog top is smooth. When you move from one pixel to the second pixel, third pixel, reflectance should not change significantly. Why? Because the fog top is smooth. Even the temperature should not change. When you move from one pixel to another, temperature should not change significantly, right? So this is the basis of the spatial homogeneity test. So when we calculate the standard deviation, if standard deviation is less, it means that it is a fog. If standard deviation is high, it means that that is not the fog. Because higher standard deviation convey that the top is not smooth. So spatial homogeneity test will remove some residual middle and high level clouds. Then is the temporal consistency check. The basis of this check is when the fog forms, it persists for some time and then it dissipates. It is not like that fog will form after 15 minutes, it will not be there. After 15 minutes, it will again be there. It's not like that. For any particular location, if fog will form, it will persist and then dissipate, right? So what we will do, we will take a particular pixel and then check whether that pixel was foggy in the initial time. See, this is a geostationary satellite, so we will have data after every 30 minutes. Suppose if I am doing this all work at 9 a.m., so I will check 8:30 image. If the corresponding pixels are foggy, then we will keep, okay, this pixel is also foggy. Otherwise, we will reject that pixel as a non-foggy pixel. So after applying this methodology and these two tests, we will finally have the fog image. So this is a daytime fog retrieval. So additionally, one more point, if you notice over here, I have written fog/low stratus image. Low stratus are basically a kind of low level clouds. So low stratus clouds are also very, thin layer clouds having the very smooth cloud top, very similar to the fog. So because low stratus cloud and the fog top are smooth, they appear very similar from the top of atmosphere where our satellite is lying. So from using the satellite data only, it is very difficult to distinguish the fog and low level stratus cloud. So here if you see, we have used only the satellite data. So if you're using only satellite data, so whatever output we will get, that will be basically a mixture of the fog and low stratus clouds. If we want to distinguish these two, we have to use some other information, but using the satellite data only, we will have the fog/low stratus image because low stratus clouds are also smooth top clouds which are very similar to the fog. So these are the few images which has been generated for daytime after applying the methodology that we have just discussed. So this is the image for 11th January 2021 at 5 UTC. So here you can see the spread of the fog in green color. The fog is there in the part of Bihar, Uttar Pradesh, Haryana, Punjab, and also some part of the Pakistan. So if we compare this image which we have generated using the our methodology with the normal simple RGB composite, that is, we took the 3-channel data and generate this image. If you see this, the here in this sea green color is basically representing the fog. So if you see this fog, whatever we have retrieved is very much close to whatever visually we can see the foggy condition. So as this methodology has been developed using the INSAT 3D data, where the data is available after every half an hour, so we can apply same methodology after every half an hour, and we can do the monitoring of the fog. So we can generate the fog at 5 UTC, 5:30, 6, 6:30, 7, 8, and so on, and we can monitor how the fog formation starts and when it dissipates, what all area it is covering. So all this is possible because the data is available after every half an hour. So not only this, nowadays we also have INSAT 3DR imager data, and INSAT 3D and 3DR imager data is acquired in such a way that we can, if we combine both the data sets, INSAT 3D and 3DR, we can have the data after every 15 minutes, right? Like 5 UTC from INSAT 3D, 5:15 UTC from 3DR, then 5:30 from 3D, 5:45 from INSAT 3DR. So combining INSAT 3D and 3DR and applying the same methodology, we can have the fog images after every 15 minutes. Now, if you see these images only, you can see at 5 UTC is a good spread. Then at 6 UTC, the fog has started dissipating. You can see from the part of the Haryana, fog has actually dissipated. Then at 7 UTC, again, there is more dissipation. And 8 UTC, the Haryana is completely cloud free, and even the fog has thinned over the UP also. Right. So similarly, you can generate for other time and can monitor the fog at various times. So completing the daytime methodology, now we will discuss the nighttime methodology. see the the daytime methodology cannot be used for the nighttime because the main reason is the absence of the visible channel. So we have used the channel over here. We have used the visible channel in the methodology. So, but the visible is not available during the night time. So we cannot use the same methodology as we have used for the daytime, right? And also simply the thermal channel cannot be used because of the low contrast between the fog and surrounding clear areas that we have already seen in this image. There is a very low thermal contrast between the fog and surrounding areas in the thermal channel. So only thermal channel usage is also not possible for the nighttime fog retrieval. So what is done for the nighttime is thermal channel is used in combination with the mid-IR channel. Mid-IR channel is here around 3.9 micrometer. So I think 3.9 micrometer channel and thermal channel, these two channels are used for the nighttime retrieval of the fog. So what is done actually is we take the difference of the thermal and mid-IR channel, and wherever the difference is positive and consistent, we call it as a foggy area. Now let's understand how it's working. So this is our thermal channel and this is the mid-IR channel. This is the part of the fog, this area. This you can see, this is a smooth area. This is the foggy area. This white patch is basically nothing but the cirrus cloud. So I have drawn a transect over here, right? And took the values over the each of these pixels, each pixels over this line and plotted in over here. So this is nothing but brightness, temperature versus the distance. Distance means from this point to this point, right? So when I plot for thermal channel, this is the dashed line is there, this is the thermal channel, and for mid-IR channel, 3.9 micrometer channel, this thick line is there. Now if you see over the foggy area, the values of BTs are over in this region. So what happens in the foggy area? As we have already discussed, fog top is very smooth. So if you see both the bands, the temperature is similar on the fog top. Temperature is similar. In the 3.9 micrometer channel, temperature is around 275 Kelvin. And in the 10.8 micrometer channel, the temperature is around 282 Kelvin over the entire range of the fog. So this is a one way to distinguish the fog. And then if you see, there is the difference between the two channel is also more or less same. The two lines are parallel, right? So wherever you will get such kind of the graph, this is basically indication of the foggy area. Now if I take the difference of two, means I will subtract 3.9 from 10.8. What I will get? I will get a positive difference. So this positive difference is basically the indication of the fog. And in case of the fog, this positive difference is also high. It is usually more than 2 Kelvin. For example, in this case, if you see, this is around 7 Kelvin. However, if you consider the case of thin fog, thick fog, all, so usually the threshold that is used in the operational system is around 2 Kelvin. Now for the other features of the land or other features like clouds, this kind of the pattern will not be seen. For example, if you see this area where the fog is not there, the pattern has inversed. Actually, if you take the difference of 3.9 and 10.8, the difference will be negative, right? So the positive difference will be there mainly over the foggy areas, right? Now let's discuss why this happens actually, why we have the lower values at 3.9 and higher values at 10. This is because clouds, fog is also a kind of cloud. Clouds has significant lower emissivity in mid-IR channel as compared to the thermal channel. Furthermore, the emissivity of the fog is lower compared to all other cloud. This is because of the similarity of 3.9 micrometer wavelength and mean fog droplet size. So I repeat, because of the lower emissivity of the fog in 3.9 micrometer channel, this difference is positive. And why the emissivity is low? Because of the similarity of the fog droplet size with 3.9 micrometer wavelength. Therefore, this difference is positive over the foggy area. Okay, and this methodology is basically called as BTD method, that is brightness temperature difference. we are taking the difference of the brightness temperature of two channels to get the fog. Therefore, this method is called as BTD method. Okay, so in this method, ice clouds like cirrus have reverse difference value. This is because of the increased transmittivity of the mid-IR channel. So 3.9 micrometer wavelength will have the higher transmittivity through the cirrus clouds, which leads to the higher BT in 3.9 as compared to 10.8. Therefore, the difference is negative. Then what is the situation of the difference in case of the clear air? In case of the clear air or the clear sky, this difference is small. It is usually less than 2 Kelvin. However, in case of the fog, this difference is large. That is usually more than 2 Kelvin. Okay, so here the methodology I have shown. So what we do, we take thermal channel and we take mid-IR channel. We simply take the difference of these two channels and put a threshold on BTD and we get the foggy image, right? So if this is the fog pattern, you can see in mid-IR channel it's slightly clear, but in thermal channel not very clear. But once you get the retrieval using this method, you will get the fog patch very clear. We have beautifully picked up the fog using this method, right? So this basically I have shown for INSET 3D imager data for 16 December 2019 at 80 UTC. That is in the 11:30 in the night. Right. So this method also works to distinguish fog from the snow-covered ground. So how the snow is removed in this simple BTD difference? This is because snow emits the 3.9 micrometer wavelength more efficiently than the fog. So if emissions in 3.9 is more, means the difference between 3.9 and 10.8 will not be positive, or if it is positive, it will be very less. It will not be more than 2. So that's how snow will also be simply removed in this difference. Then BTD method is very versatile to the type of the terrain and surface temperature over which it detected fog. It means that whether the fog is formed over the vegetation or road, building, or whatever the surface below it has a temperature, this method is capable to detect the fog. Then coming to the some flaws in this method. What are the flaws in this method? So if the surface temperature is much less than 0 degrees Celsius, then there is increase in the instrument noise, right? But still, if the temperature does not go below minus 20 degrees Celsius, fog signal is strong enough to be observed, right? So until we have the temperature up to minus 20 degree, we are able to detect it. But yes, the detection will be little difficult after 0 degree Celsius. Then second flaw is certain type of soil also gives a similar difference as the given by the fog. Therefore, we may have the false reading. Sometimes the snow is there and we may detect it as a fog. But for this problem also, there is a solution because fog is not all-time phenomena. However, soil is always there. So if we have the repeated observations and if there is a positive difference during the whole day, we can easily reject those pixels saying that these are because of certain types of the soil and not due to the fog. And the third problem in the method is some higher base stratiform clouds such as stratocumulus and altocumulus also produces the positive BTD value and hence resemble the fog, right? So this also is a false signal, but again there is a way to come out of this problem because this is the higher based clouds. So higher based clouds means this will have the lower temperature. So we can simply use our thermal channel and reject the pixels with the lower temperature. Okay. Then BTD method used in the night time cannot be used during the daytime. So why? Thermal channel data as well as mid-IR channel data would be available during the daytime also, but we cannot use the same method. Why? Because at 3.9 micrometer wavelength, we also have the radiations from the sun. We also have the solar contribution. So in the daytime, we will have the mixture of the incoming solar radiation, or you can say that the reflected solar radiation, or as well as the emitted radiations from the Earth's surface. Therefore, this channel will have the high energy and the difference will always be negative, whether it is fog or any other area. because we don't have any contribution, solar contribution in thermal channel during the daytime, but we do have the solar contribution in the mid-IR channel during the daytime. Therefore, the nighttime methodology cannot be used during the daytime. So we have different methodology. Daytime methodology cannot be used during the nighttime, and nighttime methodology cannot be used during the daytime. But still, mid-IR image can be useful during the daytime for distinguish the fog from the snow, because reflectance of the snow is much smaller than fog in mid-IR channel. So fog will be brighter as compared to snow in case of the mid-IR channel. So that's how it can be used, but direct methodology cannot be used. Okay, so these are some of the retrieved nighttime images. The upper 4 images are using the INSET 3D data, and the lower 4 images are using the INSET 3DR. So you can see the pattern of the fog, say on 16 December 2019 at 14 UTC, that is around 7:30 in the evening. You can see the spread of the fog over the Punjab, Haryana and some part of the Uttar Pradesh. Similarly at 16 UTC, 18 UTC also you can see, and then the 20 UTC. And from INSET 3D, we have, you know that after every 15 minutes we may have data. So this is the 14:15 UTC, 16:15, 18:15 and 20:15 UTC. So we, after combining both the data sets, we may have the fog images after every 15 minutes, which is highly useful for fog forecasting. Then another fog images for January 10, 2021 from INSET 3D Imager. So if you see, this is a pattern of the fog which is covering the northwestern part of UP, small part of Haryana and Punjab. So you know this type of the pattern we usually don't observe for the fog. Usually fog covers the bigger region. So we try to validate this with the RGB composite from the SIVRI. So if you see in this image, this light greenish part is basically the fog. So you can see that this part is very good resembling with whatever fog has been retrieved using the nighttime methodology. So this confirms that, okay, the methodology is working good and the retrieval is good. This is actually the foggy area only. So this is at 16 UTC, this is 16:30 UTC. Okay, so again, as already mentioned, because this is the geostationary satellite data, so we have data after every 30 minutes or 15 minutes. So you can monitor the fog, we can apply the methodology for all the times, and we can monitor, like for example, for this particular day, 10th January, starting from 17 UTC, you can see the spread of the fog, which is very less. Then fog has increased, 17:30, it has further increased at 18 UTC, then 19 UTC, 20 UTC, 21, where now it has really increased a lot. Then 22, 23, 22, 20, 30 and 23 UTC, you can see the spread of the fog over the Punjab, Haryana and Uttar Pradesh as well as Bihar. Okay, so these are another set of the images, recent images for this year. This is for 10th and 11th Jan 2022 using the INSET 3D Imager. Now here you see we have the different kind of the spread. Here we have at 20 UTC, the Punjab is covered, then 20:30, 21, 20:30, 22:30, 23, 23:30, and then 11 January 0 UTC and 11 January 12:30 UTC. Right, so again we have shown the comparison of the one of the fog map with the simple RGB composite, where again you can see that the matching is fairly well. Now coming to the distinguish between the fog and low level stratus cloud. Is there possibility that we can distinguish between the two? Because we are actually interested in the fog, because fog is something which is actually obstructing our air traffic, land traffic or railway traffic, road traffic. However, low level stratus clouds are not. But the satellite has a limitation. So what we can do to distinguish the two? We can use some visual characteristics of the fog. What visual characteristics? Fog has a flat texture, it has sharp edges and it has a pattern that conform to the topographical features like river bed or mountain valley. So I already show you that the fog always follows some pattern, like here. Here it is very clear. So it is there on the foothills. So if it is a cloud, it will be little bit elevated. So if it is elevated, so this kind of the conformity to the topography will not be there. So this kind of the things we can use to distinguish the fog from the low level stratus. And also temperature difference between the cloud top and sounding area and fog top and the sounding area can be used, because mostly the cloud top will be at the little lower temperature as compared to the fog. However, this temperature difference will be less. So, but still we may have some idea whether this is a fog or the low level cloud top, because low level cloud top will have lower temperature as compared to fog top. Then coming to some of the problems in the fog detection. When we say common detection problem, it means that common during the day and night time, right? So there are the chances when there is almost impossible to detect the fog, whatever technique we use. For example, if there is the clouds, if there is the clouds above the fog, so because we are using the visible and infrared channel, we cannot see below the clouds, right? So if there is a cloud above the fog, we cannot detect fog, whatever technique we used, right? So any information about the fog below the cloud can be seen with the continuous observation, and if there is any break in the clouds, if there is some break in the clouds, only then we will be able to see, otherwise no. And some other issues are related with the spatial and temporal resolution. Our spatial resolution of INSET 3D fog images is basically 4 km, which is not very good. It is very sparse resolution. So if there are some small areas of the fog, for example, 1 km, 2 km areas, that may go undetected. And also if there are the thin layers of the fog, that may also go undetected, because in case of the thin layer, reflectance will not be very low, very high. Moreover, emissivity will not be very less. So the difference between thermal and mid-IR channel will not be significant. So very thin layer of the fog may also go undetected. And also short duration of the fog may go undetected. Like if the fog is there for say 15 minutes only, 30 minutes only sometimes, so that may also go undetected. So these are the few common problems. Now, after discussing the methodology, just I will take a few minutes to show you some special fog episodes over Dehradun. As you all know, Dehradun is basically hilly area, so fog usually occur on the plains. Fog do not occur over the hilly areas. But from last 2-3 years, every season we are witnessing some 2 to 3 days of fog over Dehradun also. So I will just show you some days when we could see the fog over Dehradun. For example, 16, 17 as well as 18 December 2019, when we retrieved the fog. So we saw that fog was also there over Dehradun. This basically red dot is corresponding to the Dehradun area. So if you see it here, the fog is there. This green part is the foggy. So this fog is there on the 16 December. The fog was also detected on the 17 December. Now, whether our this detection from the satellite is correct or not, for that we use the ground instrument for validation. So the ground instrument that we used is basically ceilometer. So I will explain what is a ceilometer. Ceilometer is basically ground-based instrument which send a laser signal in the upward direction and then receive the backscattered energy. Right. So when it sends the laser signal, so wherever it will find some droplets, particles, it will send the backscattered signal. If it will not find any droplet, then the signal will simply pass to the high level of the atmosphere. So if the backscattering is low, it means that some small particles or small number of the particles are there. However, if backscattering is high, this value, if you see the backscattering is high, it means that some large intensity of the particles are there. However, in case of the fog, which is a cloud, the intensity of the backscattered will be very high. It will go beyond this range and will be appearing white in the plots. Now let's see the plots. This is the ceilometer plot for 16 December 2019. This is the height, that is altitude versus the time. So when it says 16 December 2019, so it is starting from 5:30 a.m. to next day 5:30 a.m. So if you see here the backscattering values, so we are interested in the low levels only because fog is at the lower altitude. So if you see here the backscattering values are low around 200, then little bit high to 2000 and all. But here about we can say around 6 p.m. 7 p.m. That is here this is 5:30, 6:30 around 7 p.m. If you see the backscattering is white, means this is a very high backscattering at the surface itself. So this is basically corresponding to the cloud present at the surface itself, and the cloud at the surface is nothing but fog. So this data is basically at the Dehradun only. So this further confirms the presence of the fog from say 6 p.m. on 16 December, right? So this fog persisted the whole night, also till 5:30 a.m. on next day. Then if you see the 17 December plot, 5:30 a.m. again the fog is there. So this fog actually persisted up to around 9 a.m. next day. The fog which started at 6 p.m. 16 December, it persisted up to 9 a.m. on the 17 December over Dehradun area. Then during the day again the dissipation of the fog occurs, that because of the presence of sunlight, right? Then again in the evening on the 17 December fog start formation, right? Again at around 6-7 p.m. there is a foggy area. This white at the surface indicates the presence of fog. Then again it persisted, and it also persisted on 18 December around till 9:30 a.m. And again during the daytime there was no fog, but again in the evening at around 4-5 p.m. only this day the fog started, and it persisted till 5 a.m. next day. So these were the 3 days in 2019 where the fog was there over the Dehradun, right? Now this instrument, it gives me additional information. It does not give me only the presence of the fog. This instrument is also giving me the information of the thickness of the fog. See, this is the height, right? So if I can see the thickness of this cloud is this much. This much means it's around 100-200 meters, right? This level is 500 meter. So this is around 100-200 meters. So thickness of the fog on 16 December was around 100-200 meter. However, on 18 December, if you see, this is about 300-400 meter, right? So from the ground-based instrument, we not only detect the presence of the fog, we can also detect the thickness of the fog in the vertical direction. So in every season we actually witness the presence of the fog for 2-3 days. So then another example I want to show you is that during January 10-11, 2021, these are the fog pattern at the different times. Here again this red dot indicates the location of Dehradun location, right? So if you see this fog patch is there at 16 UTC, 17, 18, and it had persisted up to 22 UTC. Again, we validated this information with the ground information. So here I have shown you the information, simply the visibility information, right? So this is a visibility plot, visibility with respect to time. So this 10 Jan 06 means 10th January 6 UTC, then 10th January 9 UTC, 10th January 12 UTC, then 10th January 15 UTC, right? So 10th January 15 UTC, starting from 10th January 15 UTC when the visibility is about 100-200 meters only. So this indicates the presence of fog. However, before that the visibility is 2000 meter, which indicates that there is no fog. So fog is there from 10 January 15 UTC to 11th January 3 UTC. So this all graphs also show you the presence of fog over Dehradun, which is being validated with the visibility information over Dehradun. So this is all from my